Good morning, I am Shaad. Today we are going to see application of finite automata in search engines. Searching for information in large repositories or the internet employs the concept of string searching. With the World Wide Web expanding with databases from diverse fields, it has become a growing concern for database curators to find an efficient searching algorithms for the tasks. In comparative terms, the power of an algorithm over another is in its time complexity and efficiency of operation. A lot of algorithms have been designed for the task of string searching. Also, some of the fast string searching algorithms were developed based on the deterministic finite automata (DFA), which prompts the need to thoroughly research and investigate how this principle is applied. Today we are going to analyze the searching power of DFA. The DFA approach is used to overcome the problem of backtracking, thereby improving the time complexity, the speed and efficiency of search based on results obtained. But before we begin, let's see some amazing research work in algorithm written in the past. In 1956, Stephen C. Klein proved the equivalence between finite automata and regular expressions, which led to solving the string searching problem in time linear order, big O of m plus n. For a long time, many string pattern recognition problems were formulated in terms of finite automata. This approach reduced the string matching problem to a language recognition problem. In 1970, Morris and Pratt came up with the first linear time algorithm to solve the string matching problem, which preprocessed the pattern in big O of m and searched the text string in big O of n plus m time. In 1977, around the same time that Knuth, Morris and Pratt came out with their algorithm, Boyer and Murray proposed an algorithm that pre-processed the pattern in big O of m plus mod sigma, where mod sigma is the alphabet size. It used n by m number of comparisons and searched the text in big O of m plus n in the worst case. In 1980, Horspool brought forward an algorithm which showed that search speed can be enhanced by comparing first the character in the search pattern that occurs least. In 2012, N. Singla and D. Gurg wrote applications of string searching algorithms and their areas of optimal performance, and the algorithm of choice for text editors, digital library, and search engines in the Moore-Bure algorithm. Now let's see how actually DFA do the string searching and how it works. So a finite automata such algorithm follows certain steps such as constructing a DFA for the pattern, performing the search. Each character in the text is examined just once in sequential order. When searching is done, a state transition table for the automata is created to represent the state transition function. Given a text t equal to t1, t2, t3 till tn, where I represents the index of the text symbols such that I is from 1 to n, and pattern p equal to p1, p2, p3 till pm, where j represents index of pattern symbols such that j is from 1 to m, where m less than n and m and n are the lengths of the pattern and text respectively. So this is the algorithm for the DFA searching. There are certain steps. The first one is construct a DFA for the pattern. A DFA constructed for the pattern will be one state longer than the length of pattern, so the DFA takes m plus 1 states, which ranges from 0, 1 to till m. Let k represent the index of states such that k is from 0 to m. Initialize start state to be 0 and final state to be m. Initialize start and last index of text to be 1 and n respectively. Let I represent the index of text such that I is from 1 to n. Initialize start and last index of pattern to be 1 and m respectively. Let j represent the index of pattern such that j is from 1 to n. Second, performing the search. Starting at state k, read each text symbol against first occurrences of pattern symbol to check for match. If match, increment k to k next and read the next text symbol. The DFA will be in kth state if the symbol of text have been matched with jth symbol of pattern. If the next ith text symbol matches the corresponding jth pattern symbol, then the automata will transit to the next kth state, that is delta of k current ti equal to pj equal to k next. Otherwise, it remains in the current kth state, moves to the state or the other states not exceeding in the current kth state. Next, if all jth pattern symbols were found in sequential order in any ith location of text, that is k equal to m, final state has been reached, then announce match success. If all jth pattern symbol could not be found in any ith location of text, then we will announce that match is not found. No match has been found. Next, creating the transition table. Create table for all states from k0 to m, as k from 0 to m, from the transition function for each and every element. So in the automata diagram shown in figure, pattern preprocessing is carried out as each text symbol is scanned. Once against the pattern symbols, the text is scanned from the shortest prefix of the pattern through to the longest prefix, that is ABAA. Unless we get to state 4, the pattern is yet to be found. Here, the automata remains in state 0, which is the empty string prefix of the pattern. At state 0, we input the first symbol of text, A, and it matches pattern prefix of length 1A. So we can move to state 1. If we put B as the input, the automata would still remain in state 0. At state 1, we input the next text symbol B and it matches the pattern prefix of length 2AB and it moves to state 2 or remains in state 1 if A is entered as input. At state 2, A, which is the next text symbol, is entered and it matches the pattern prefix of length 3ABA and it moves to state 3. If B is entered, it moves back to state 0. At state 3, the next text symbol P does not match the pattern prefix of length 4. So the automata moves back to state 2. At state 2, we enter B, which is the next symbol of text, and it moves to state 0 since it still does not match pattern prefix of length 2. Again, at state 0, we input A and the automata moves to state 1 and still remains in state 1 since the next text symbol entered is A. Now we enter B, A and A from the text symbols, which allows the automata to transit to state 2, state 3 and state 4. At state 4, where pattern prefix of length 4 ABAA has been matched, we can announce match success since the final state has been reached, but searching continues until the whole text symbols are exhausted. At state 4 again, if we input A, the automata moves to state 1, and if we input the next text symbol B, the automata moves to state 2. This whole process continues until the text is exhaustively searched. A transition table is created for the data as is required in DFS searching algorithm. In this table, the underlined symbols in the text column represent text symbols that match pattern prefixes, while the italicized symbols indicate the current text symbol that is being compared with the pattern. The bold and underlined symbols at the 11th row in the text column signify where a match is successful. This is the state transition table for the sample data. Conclusions. A solid conclusion can be made from the analysis that the most efficient solutions for the string matching problem are based on finite automata. The ability of the finite automata to eliminate the problem of text backtracking has influenced the development of the first linear order string searching algorithm. Because it also preprocesses pattern in big O of m time and runs a search in big O of n time. The DFA today used as a tool for string searching because of its efficiency. Among these are the Knuth-Morris-Pratt and Boer-Murray algorithms, which are based on DFAs. This was all about application of DFA in search engines. Thank you for staying till now. I hope you liked this presentation. Thank you.